Hello again, everybody, and welcome back. We're going to be starting Chapter 10 today with momentum and collisions. And we're going to define momentum in just a second right here. But collisions are kind of interesting because it could be a couple different kinds of collisions. Like you've seen collisions between like billiard balls, how one stops moving and the other one starts moving. We call those elastic collisions. Other kinds of collisions maybe like inelastic collisions that we'll define later. Things like what happens when two cars hit each other and crumple up and that kind of thing. But it's all based on the idea of momentum. So before we go any further, let's just go ahead and define that. So momentum we define mathematically as simply the product of an object's mass times its velocity. This P right here is momentum. Now, we couldn't use M for momentum, right, because mass already has that. So, for whatever reason, P was picked for momentum, but you'll notice that it has this arrow over top of it that indicates that it's a vector quantity. It does have direction. So you can have positive or negative momentum, or well, any object can have a positive or negative momentum, depending on what your coordinate axis is. Why is that? Well, because any object that has mass has some velocity, even if that velocity is zero, all right? Well, zero velocity would have no direction, but any other velocity, any non-zero velocity would have a component either in the positive or negative direction, which is why the momentum is in either the positive or negative direction. Okay, so its direction does matter. The units for momentum are kilograms meters per second, and if you think about it for a second, well, what's the unit for mass? That's kilograms, right? What's the unit for velocity? That's meters per second. And there you have it right there. That's where our units come from, kilogram meters per second. So that's going to be our value for momentum or for changes in momentum. Either way, it's kilogram meters per second. All right? So now, momentum behaves a lot like work. Remember how we added up work before? How we said the whole total work is work 1 plus work 2 plus work 3, all right? And you can have positive work or negative work depending on what was happening to the object. Well, the same thing is true right here. You have momentum 1 plus momentum 2 plus momentum 3. So the total momentum for a system of objects, that is ignoring the whole other rest of the world, but if you're just looking at the system of objects right here, the momentum, the total momentum, is going to be the sum of the momentum of object 1 plus momentum of object 2 plus momentum of object 3, and so forth. You simply add them all up, and that'll give you the total momentum. And what we're going to find later on is that total momentum doesn't change at all. It's going to be constant. Okay, so remember a while back how we defined Newton's second law, and that is the net force on an object is mass times acceleration. Right? Well, that's kind of our general guiding equation for all of Physics 1 right here. But it's actually sort of incomplete. Not really incomplete, but it's conditional. That is, assuming objects have a constant mass. All right? So if you've got a force on an object that has mass, it will accelerate at a certain rate. All right? But what if that mass changes? That mass gets greater or gets less? Objects don't generally gain mass. Well, I guess they could. But many objects lose mass. Like, for example, let's say you have a rocket, all right? A rocket blasting off into outer space, all right? And it runs on fuel, right? Well, that fuel tank right there gets less and less and less and less as the fuel is expended, and so the mass actually changes. So Newton's second law, this right here, F is equal to ma, is kind of incomplete. Or like I should say, conditional. What's actually more complete is really Newton's second law as described by momentum. All right, so let's take Newton's second law, F is equal to ma, and change it around just a little bit. Okay, we know that net force equals mass times acceleration, and we know that acceleration is, how do we define acceleration? It's a change in velocity over change in time. All right, well, let's look at that top part right there. What is that? M times change in v. That's our definition for momentum, right? Or if the velocity is changing, we would call it a change in momentum. I should have put a vector arrow over that v right there. All right, because velocity does have direction. All right, so what that means is we can define the net force on an object is as the change in momentum over the change in time, and that's exactly what that tells us right there. All right, so it's really not changing anything, it's just looking at it in a different way. All right, this is more general, and this is even valid if the mass varies. All right, so the momentum of the rocket that is going this way and the momentum of the gases and the fuel that is expelled out the back is going to be the same, and so you can actually figure out what the velocity of the rocket's going to be, even if the mass changes or the mass varies. So that's kind of a good application of Newton's second law, just looked at through a lens of momentum. Okay, so let's go ahead and apply this to problems that we probably would have solved using kinematics in the past, but we can now solve using Newton's second law and the idea of momentum. Let's change colors here. All right, so we have an apple in a tree, okay? And I'm just going to make a blue tree right here, and here's our apple, and it falls down to the ground like that, all right? It has I want to say it has a mass, but it doesn't. It has a weight of 2.7 newtons, all right? So that is really the weight force, right? That is mass times the acceleration of gravity. That is mg right there. So that's the weight force. And it falls vertically downward from rest for 1.4 seconds. So that is our time right there. So the question is, what is a change in the apple's momentum per second? All right, well, we just said a minute ago, the net force on an object equals a change in momentum. Oops, I'm messing up down here. Change in momentum per second. All right, well, the question is, what is the change in the apple's momentum per second? Well, what that comes out to be is, what that's asking you is, how much is the momentum getting greater and greater and greater? Because as you know, apples, as they fall, as anything falls, the velocity picks up, and so you've got greater velocity for a certain mass, so greater momentum, so more and more and more momentum. Think about it this way. You'd rather have an apple hit you on the head from 1 foot up rather than 10 feet up, right? Because it has less momentum when it's only dropped about 1 foot. So the momentum is changing per second. At what rate? We have it right here already, right in front of us. We don't really even need to calculate very much. All right, the net force, that is the weight force that's pulling it down, I'm trying to write with my cursor again, 2.7 newtons equals the change in momentum per second. And that's our answer right there. All right, it's 2.7, well, we say 2.7 newtons, but if we want to put that into momentum units, it's 2.7. What's the units for momentum? That's kilogram meters per second, and then divided by second again. It's really kilogram meters per second squared right here. All right, that is the value, that is the rate. This force right here, the net force, is the amount that the momentum changes per second. So a newton, and we defined this a couple chapters back, is kilogram meters per second, meter per second squared. That's really the definition of a newton. All right, change of momentum over time right here. We tend to call it newtons because it's a little more convenient, but that's another way of stating a newton. It's a change of momentum per second, all right, over per unit time. So part B, we're actually going to do a little more calculation here. Part B is asking, what is the total change in momentum during the 1.4 second fall? See, we didn't want to use the 1.4 seconds here quite just yet. It was asking us, what's the change in Apple's momentum per second? But part B is saying, okay, over those 1.4 seconds or any other span of time, how much does the momentum change? So if the net force equals a change in momentum per second. Oh, vector arrow. Okay, so the question then is, what is the total change in momentum? All right, well, you probably know what to do here. We'll just take our seconds and multiply it up, right? So our change in momentum total over that amount of time is a net force times, I've been writing S for time. I should be writing T, I guess, right? For time right there. Yeah, sorry about that. Time. All right. So this is net force times time. In the previous ones, we didn't really need to worry about time, but here we do, because it's a certain amount of time. That's 1.4 seconds that it's falling for. So what is the net force? 2.7 newtons, right? It's the weight force, and the amount of time that it falls for is 1.4 seconds. So what does that come out to if we multiply 2.7 times 1.4? That gives us 3.8. What is the units for momentum or change in momentum? It's kilogram meters per second, and that's our final answer. All right, so momentum is mass times velocity, but it's also got a relationship between net force and time as well, which we just demonstrated right here. All right, so that's example 10.1, and that's going to be it for now. There's a couple problems, obviously, in the problem sets that pertain to this, but also pertain to the mass times velocity definition of momentum as well. If you have any questions, please make sure you come see me. But in the meantime, thanks for watching, and I'll see you on the next one.